I'm just going to talk about EEE Lab 4 Part 1. We need to require to develop a more step machine which provide this sequence under control chain input, which is enable output to motor remain fixed, and we can control the clockwise or the anti-clockwise, and also the red for stepping the motor. So this is how with the table, the flip-flop excitation table presents state 0, 0, and this is flip-flop input. J is 0 and X is K is X, and followed by this, and this is the one diagram, and this is for S1, S0, S0, and this one, and the output will be 1, 0, 0, 0, S1, and the next step will be 0, 1, and the output will be 0, 0, 1, 0. For S2, next step will be 1, 0, or 0, 1, and the output will be 0, 1, 0, 0, and the last one S3 will be 1, 1, and the flip-flop input will be X0 and X1, so output will be 0, 0, 0, 1. So this is the table for JB, KB, JA, and KA. So output, so overall the output will be A prime, 0, 0 will be A prime, B prime, 0, 1 will be A prime, A, B prime, 0, 2 will be A prime, B, and the last one 0, 3 will be A, B. So we will be using NAND get, AND get, and this one no get, and also HC1077 to build this more step machine. So this is how our circuit make design. So now it's going clockwise, which is from left to right. So now we need to make it to anti-clockwise, which is right to left. So we press this to control it to clockwise. Okay, now I release it and back to clockwise, and this is to the red one. Make it faster. Okay.
Hi guys, so now I will be showing you Lab 4 Part 2. So in this part, we will be using two schematic diagrams. One is for the 3-bit LFSR and one is for the 7-bit LFSR. And as you can see here, this is the output that we have predicted, and it should be running from 010 to 101, and then to 110 to 111, and then to 011 and to 001, and then to 100, and then back to 010. So as you can see here, it's actually running from 010, 101, 110, 111, and 011, 001 to 100, and then back to 010. Is looping in this series, and when the button is pushed at 001, it will turn to 000, and it's looping in 00. And when we press it again, it will loop back to 100, and then start looping in this series again. So in this oscilloscope, the blue line indicates the frequency and the yellow line indicates the S2 output that we are using. And as you can see here, the output seems to be showing a random pattern. As you can see, it's running in a random pattern, but this is called a pseudo-random, which while the scale is not large enough, it was showing a random pattern. But when we turn the size bigger, it actually shows a constant pattern like this. As you can see, the pattern is going in the same pattern. So this is where the pseudo-random occurs. It's not actually a random pattern, but when the scale is not large enough, it seems to be a random pattern. Yeah, that's it for this part. In the second part, as you can see at these two diagrams, we are actually moving only the Q1 and Q2 to the Q6 and Q3, just to make sure that our bit is starting from X0 to here to become X7. And the exclusive OR gate, we are using the same port. So this is our schematic. As you can see that in this oscilloscope output, we are actually getting a random output for this part.
Okay, hi, I'm Brian. I'll be talking about part 3 for this experiment. Okay, so for this part of the experiment, we designed a milli-step machine to detect the sequence, which is 011. Okay, for this milli-step machine, right, it will detect the overlapping sequences also. So we implement the design from part 2 by adding a step machine and step machine using D-type flip-flops and few NAND gates and XOR gate to test the circuit. So as you can see here, W is the input from the part 2 LFSR, and it will run through the step machine, and the output would be F. So for this is our diagram for this part of the lab. So when it's idle, right, the correct the output we want is 011, so the first one should be 0. But when the first output is 1, it will look back to idle, which is the overlapping sequences. So when it's the correct output 0, it will move to F0, and then another correct output, which is 1, it will move to F01. But if from at the second part, right, when the output is 0, which is the wrong input, it will look back to F0. Then the correct input will move to F01. But when at F01, when the output is wrong, which is 0, it will move back to F0. But if the correct output, okay, so this is our table for this part. This one, first row is idle, second row is F0, third row is F01, and the third one, which we don't care, is F011. Okay, so this is K-map for this part. Okay, so as we assume, DA would be BW, DB would be W0, and F would be AW. As you can see here from the diagram, DA is here, and then the input is BW. We don't have a AND gate, so we use 2 NAND gate to make AND gate for this experiment and for this lab. Okay, and you can see here DB is W0, which is here. We only have W, but we use the XOR gate here, and then the second input we connect it to VCC to make sure it's always high, and then and like that we get W0, and then F, which is the output, is AW. As you can see here, A here, and then W is from here. Okay. Okay, so this is a circuit for part 3. Okay, as you can see here, right, the output we want is 011. So this flag is the clock, which we actually don't need, but then I put it here so it will be easier for us to see the frequency. Okay, so we can start here, 0 and then 1 1. You can see again. Okay. Now it's 0, 1, 1. It'll look back to 0, which is idle. Okay. Okay. Stop. Okay. So due to certain time constraints, right, we do not have enough time to take all the readings during the 2-hour lab session. So I took the oscilloscope image from my friend. Okay. So as you can see here, right, this one. The yellow line is the input, which is W, and the blue line is the output, F. So you can from here we will start from here. Okay, so when the first one is 0, so okay, the output will maintain 0. As you can see here, output is all 0. Then when it reach reach 011, which is here, the output will be 1, and then it will move back to either when the input is still 1, as you can see from here. Okay, so that's all.